is electromotive force. And internal resistance. Got that? Yeah? Yeah? Okay, continue. So, let's start with EMF, I think. No, actually, sorry, let's start with potential difference. I talked about this before. It's just really another word for what? Voltage, yeah, it's just another name for voltage. I don't think voltage is used so much. I think most people nowadays would say PD, potential difference. Really, it's just another name for that. I think you know that already, but I would like you to write it down. Yeah, potential difference. Yeah.
And 5 PD equal 5 voltage.
Yeah, yeah. Okay, got that? Yeah? So, electromotive force called EMF. What is that? Now, you don't need to write all of this, so first let me show you what it is. So, EMF is the voltage developed by any source of electrical energy, such as the battery. That, now, before you write, that's really what you need for the exam. EMF really is just the voltage of the battery. That's really what it is. Now, it's generally defined as the electrical potential for a source. So I say a source. It doesn't have to be a battery, but I mean usually when we look at circuits, that's where the power is coming from, is a battery. A device that supplies electrical energy is called a seat of electromotive force, or EMF. And EMFs convert chemical and other forms of energy into electrical. But again, you know this, like if you have a battery takes chemical energy and gives you electrical energy. Yeah. So what do you really need for the exam? Really, you need this. Electromotive force is the voltage developed by a source of electrical energy, such as a battery. Got that, Bruce? You wrote all of that? Really? Honest? Okay, I believe you. Right, do you have that? Yeah?
Yeah.
So when I say, for example, here, when we talk about like, come on, the EMF here, for a battery like this, it would say it on it. So this, for example, is 1.5 volts. That means it provides 1.5 volts. So, you know, not too difficult of an idea. Now, how do I put this back in? Okay. So let's continue. So what exactly is the difference between EMF and PD then? Well, EMF of 1 volt means each coulomb of charge is given 1 joule of energy. So, for example, this battery here, when a coulomb goes in, it comes out with the ability to do 1 joule of work. Whereas a potential difference of 1 volt means, between 2 points, means each coulomb could do a joule of work, and it did do a joule of work. In other words, what I'm trying to say is EMF provides a voltage, whereas when we say potential difference, we usually mean the voltage was lost, like the potential difference of a light or the EMF of a battery. You see, so really the only difference really is EMF gives and PD takes. That's all. But they're both voltage, you know.
Then EMF is the bigger than PD.
It should be in a circuit, yeah. It should be, yeah. Come on. All right. Now, the circuit below. Before actually that, let me just draw a little picture here. Let me just make sure I'm recording. Yeah. Here is my battery. There we go. We'll make it 4 cells. 1, 2, 3, 4. So in our mind, we picture the battery like this. Yeah, something like that. But there is a problem. You'll notice with a battery, it sometimes gets warm. Have you noticed that? Like with your phone or your laptop, the battery is sometimes warm. The battery is not a perfect provider of electrical energy. It will waste some energy. So we imagine it's like there's a small resistor inside the battery. Now, please, it's only like this. There's not really a small resistor inside the battery, because if there was, we would just take it out, obviously. So what I'm saying is, this is our model. This is how we imagine a battery. That in some sense there's a perfect part, and then there's this resistor which we don't really want. And it's this resistor that might produce the heat and waste the energy. You understand? So this part here provides the EMF, whereas this part here is called an internal resistor. Okay, so I would like you to draw this, because this is the picture we have of a battery.
Why the battery needs the internal?
No. The internal resistor is not really in it. It's like we imagine it's like an internal resistor. There's not really one in it. There's not really one there. It behaves like there's one there. Yeah? Okay. Have you drawn that? Yeah? Now, our job is we would like to know what is the size of this internal resistor. Now, we have a small problem. It doesn't really exist, so we can't just take it out and measure it. But there is a circuit that will help us here. So, oops, I'll get my pen back. So let me just put this in a circuit here. And I'll just connect it up to a resistor here. And this resistor is there. Now, just before I continue, whoops, if I put a voltmeter here, it will give me the voltage, the potential difference across the resistor, true? Is this the same or different? Same, yeah. Same or different? Same. Same or different?
Which one? What is it?
Same as what it was at the start or different? Same. So if I put it here, same or different? Same. And if I put it here, same. So the reason I'm doing this is because normally for these circuits, the voltmeter is actually connected on what's called the terminals of the battery. These are called the terminals. So we usually put the voltmeter here. And although it's giving us the voltage here, it's really the same as this. It's as if the voltmeter is here. So in other words, this is telling me the voltage here. But that is going to be the same as the battery anyways, because there's no other resistor, so this should match this anyways. I just really wanted to make the point that although we put it here, it's like we could put it here too. Yeah. Okay, what else do I need in my circuit? Of course I need a switch. So let's put in the switch. I would like an ammeter, so let's stick an ammeter here. I have my voltmeter. Let's put it here. And I'll make this a variable resistor. So this is my circuit. I'd like you to draw this and we'll explain why it's useful. I wonder actually if I drew it here. Oh, I did, yeah. I just put my voltmeter, underneath, but it's neater, I'll put on the top. Terminals.
Does the ammeter and the voltmeter always...
It does, yeah, it does. Although, fortunately, it's quite small. Okay, have you drawn that, Bruce? Have you drawn that?
Of course.
Great. Now, let's use Kirchhoff's laws here, okay? So, who will I pick on? I think I'll pick on Darius, since you have the pen in your mouth. You drew my attention. Can you give me Kirchhoff's loop law, starting here, and we'll call this E. So, loop, please. Which way are you going to go, left or right? Okay. Yeah. Okay. Oh, I'm picking on the right person, making you sweat now. What have we got next? What's it? IR. Yeah, because it's the voltage for this one here. And then finishes where? Yeah, the small one. Yeah. So we can get this equation here. Yeah. Now, if you wanted to, you could also write it like this: E minus, because we know what the IR is. The IR here is the V, because we know the voltage here. So you could actually write it like this, if you wanted to. Yeah. Now, which things do we not know, and which things could we know here? Which thing in this equation do we not know, and which thing do we know?
We don't know.
We definitely don't know small r. Correct. We definitely don't know this. What else may we not know, or do know? What do we not know? Yeah, well, just looking at this equation.
E?
Yeah, we might not know the E, but what should we know? Well, we should definitely know V, because where do we get the V? The voltmeter. And we definitely should know I. Where do we get the I from? The ammeter. Yeah, yeah. So, because the V and the I, we don't know it, there are variables. They're the things that change, so there are variables. And the E and the R is constant. The E doesn't change and the R doesn't change. That's useful. Now, let's imagine we change this. What happens when I change the R? Does the V change? Yeah.
Yeah.
And will the I change?
Yeah.
Yeah. So we want to make a graph, and we have two choices, and each graph has an advantage and a disadvantage. So the first thing we could do is make a graph where we put V here and I here, and the second thing we can do is make a graph where we put I here and V here. Let's see what each graph would represent if we were to plot the V and the I. So first, I could take this and change it into V equals E minus IR. Yeah? Which I can write as V equals minus or I plus E. So this is a graph like Y equals MX plus C. So this graph will be going down, But what does the slope of this graph tell us?
minus R.
The slope is equal to minus r, isn't it? So what does the r equal? Minus the slope. Now that seems very useful. Also, what is this point on the graph?
R equals R.
Yeah, so what is this?
Oh,
It's the E. So this graph seems very useful, doesn't it? Now let's have a look at this graph. If we plot it the other way, if we put the I here, so we can get, let's see, where am I? Here. E minus V equals I or. So I equals minus 1 over or V plus E over or. Yeah, so this graph, it's also useful, but it's a little bit messier because it's also going down. The slope for this graph would be minus 1 over r. So the r would be minus 1 over the slope. So, that's fine as well. In the exam, when this question has come up, they didn't tell the student what to put on the x and what to put on the y. So I kind of want to put the v on the x because the v is the thing that you change. And normally in physics, the thing that you change, you put it on the x-axis. However, for this graph, it's just so much more convenient to put the v on the y-axis because you can get two things quickly and easily. We can get the or, and we can get the e from the graph. So, what I would like you to do, I think, let's see what I got here. Yeah, just so you know, this formula is in the formula book. EMF equals I, R plus R. But, as you can see, it was more useful to replace the IR with the V. Now, you can still use this equation. This is useful as well. So I'll just summarize it here. There's two ways to write this equation. The first way is like this. E minus V minus IR equals 0. And how did I get this one? I used what? I used the loop rule. Okay. But the second way is if I use the loop but don't use V equals IR. I can get this formula, which I write as E. If I take these over to the other side, equals I or plus or. Okay, and this is if you used the loop but not V equals I or. This one here is really good if we want to make a graph. This one here is actually this is useful in the exam when they give you when do you use this one? Yeah, when they give you I and or. Because sometimes in the exam they might give you the I and the or. So normally I would see this question in section B and this one here in section A in the exam. Because this is short but this one takes time. Can you write this down? I know there's a lot on the screen. You don't have to write everything. What I really, really want is this. I would also like you to write this graph down as well. And of course the circuit, which you should already have.
What about the y equals an axis?
No, that's okay. That's just me explaining. This is the key result here. Have we got that? Yeah? Did Connell give you any timetable for next week? He's leaving you guessing when your exams are. Interesting strategy. Well, like I said, he told me that physics will be the last day, because I think that's when the biology is. It is, yeah. Did your chemistry teacher tell you when the chemistry will be? It's Thursday. Oh, so you know. What about EAP?
We don't have.
No more, you finished it, okay. Dennis said he'll tell you on Monday what your active listening topic is.
They're always set on Monday.
Yeah, excited. What did I pick? Now you are. You're curious. You want to know.
No.
Did he give you any clues?
Are you going to give us an excuse?
We used to.
It will be big.
How big?
In terms of what?
No. Once Dennis tells you on Monday, you'll understand why I said that. I'll tell you now, it will be big.
Can you do 5 squared?
No. No, it's much better this way. Trust me, when he tells you on Monday, you'll be going, oh, Stephen. And then when you start shaking your head, he'll say, why are you shaking your head? Oh, Stephen. It's a clue. Huh? You'll find out on Monday. I'll just tell you, it will be big.
What does it mean big?
Oh, no, you'll find out on Monday.
It's big topic.
No, it's maths.
Math?
And it'll be big.
What does it mean big?
You'll see on Monday. You'll see on Monday. Okay. So, we already had a look at the two graphs, and we talked about what you can get. So here's an example. I have two examples to do. One is using the graph, and the second is by using the other way to write the formula. So let's start with the graph. If you can copy this table and then make a quick graph, and I'll make it in the graphing program here. You got that, guys?
Yeah.
How come they take the business people's opinion and whether they want a physics subject or not?
We can't. It's not their fault. They're not as smart as us. Okay.
No,
The topics I wanted to pick was too advanced for them. We should have pity for them. We should feel sorry for them. Well, they were hard, but because the business students, I had to change it. Yeah. Now she's wondering why do they have a say? But I said they should have our pity. They can't understand the true beauty of maths and physics. It's a shame. It's a real shame.
Why?
I don't know. It's just some people are born with some gifts and some people are business students. Anyways, we'll continue. We won't worry about that. Okay, did you copy that down? Yep. Right. What am I putting on the X? The current. Yeah, so I'll put the current in first, and then the potential difference in volts. So what's my first current here? 1, is it?
Yes.
And does it decrease by 0.1 each time, is it? Until 0.1. And then what's the voltage doing?
0.1.
It starts at 0.1?
Yeah.
And increase by 0.1 as well. Okay, that's fine.
No. Yeah. No. Start is 1.
Oh, start is 1. Yeah? Like this?
Yeah.
Okay, let's make the graph here. Insert chart. Scatter, and then I shall pick title. It is voltage. No. PD against current. Current in amps and potential difference in volts. Right. So you can just roughly copy something similar in, please. Now I'm going to be pig lazy and not calculate the slope. I'm just going to have the program do it, because we did this recently, the y2 minus the y1. So let me just be lazy and get the program to do the work for me. So here is the equation of this line. We can see what the slope is. What's the slope? Minus 1. And what is the C?
Plus 2.
2. So that's quite convenient, because what is the internal resistance?
Minus 1.
1 ohm. And what's the EMF of this battery? 2. So this one graph can tell us two difficult things to know about the battery. We can know the battery's EMF, and we can know the battery's internal resistance. So the OR is 1 and the E is 2. Is that okay, guys? No? What's confusing you? How I got this?
Yeah, that's the slope, right?
The slope is the coefficient of the x, so that's minus 1 is the slope. Yeah? I didn't bother the program calculator for me. Yeah? And this C here? Oh, I thought you said you fixed this for me. You told me exactly what to do. Didn't you? Yeah, the internal resistance is equal to minus the slope, and the slope is minus 1. Is that okay?
Where did you get the 2 from?
The 2, if I had graph paper, it'd be a little bit easier, but what you do is you extend the line until it hits the y-axis, and that's the C. Yeah. Is that okay? Yeah. So we can say that the OR is 1 ohm and the EMF is 2 volts. Do you want the EMF to be big or small? Probably want it to be big. And the OR? You want it to be small. Okay. Continue? Yeah? Any other questions on this? Is okay? Yeah. Of course, I don't see this usually in section A. This is a section B question where you have to use graph paper. But the next example, this is like a section A question. So what happens here is you have a battery with an EMF of E and an internal resistance R, and it powers a resistor of 2 ohms. And when you're using 2 ohms, you get 500 milliamps. But then when you increase the resistor to 3 ohms, you get 400 milliamps. So what I'm doing here, where's my picture gone? Yeah. Here I use 2, then 3 ohms, and then I see that this changes. So I tell you the 2 resistance values and the 2 current values. So by using my second equation, which is really the same as the first one, just with the replacement of the V, you can get the OR. Now I would like you to try this before I do it, because I think you can do it by using this formula and the information in the question. I think you can do this. We getting answers? You got an answer over there? No?
1 minute.
You think you can? 2 minutes? Or two answers? You have an answer there? Yeah? Are you sure?
Yeah.
Sure?
Yeah.
Very sure?
Sure.
Okay. Let's have a look. Continue? Continue? Let's have a look. So, my formula I said to use is E equals I or plus or. Now, in the beginning, what's the or? It's 2, isn't it? So I have E, and what's the current in the beginning?
500 by milliamp.
Yeah, so 0.5. 2 plus or. Then I change the or. So I have E equals 0.43 plus or. Now look at what you have. This is your normal maths problem. How many equations? 2. How many unknowns? 2. 2. E and or. What's the easiest way to solve this?
Divide.
No, easier than that. Equals. What's the verb to make something equal?
Okay.
Not quite. Not quite. Say, what is it? Go on. Now what you say? You're not too far away. No, she's actually close with it. You want to make the verb of equal. No? What is it? Say again? Oh no, that's too difficult. No.
Combine.
No, it sounds like equal. It's just you change the form.
Equilibrium.
Equilibrium, no. And we don't know this word. I think you do. Equations is a noun. Yeah, we need to make the verb from equal. Equationate. No. I do like equationate though. We want to equationate the two equations. Equation 5. Oh yeah. Yeah, we need to equationify them. No, not this. Good try though. Nobody knows. Come on. Somebody knows. I know. Okay, I'll tell you. And as soon as I tell you, you'll go, oh yeah. Equate.
Equate.
You don't. This is a new word.
Yeah.
Is it? So new. Alright. We equate them. So we got 0.5. But I do like equalify them. Well, I can't say equalify, that's not a word. But I do like it. 2 plus or equals 0.4 3 plus or. Okay. Got that? I think this is probably what some of you did. So when we multiply this out, this will be 1 plus 0.5 or equals 1 plus 2 plus 0.4 or. So that's 0.1 or equals 0.2. Yeah, so then you get or equals 2 ohms then. That's what you got, and that's what you got, I heard. And any look over here? Yeah? So, like I said, this is like a section A question for this topic. Sometimes, of course, they also ask for the E, which is easy now because you just put that, let's say, in here. So 3 plus 2 is 5. 5 times 0.4, is that also 2? By coincidence, it's also 2. Coincidence.
Yeah.
Equate. What wonderful words we have today. Yeah. Okay. So, I think there's a few minutes left. Yeah. So, I think there's a few, 2 or 3 questions there. Is there? Only 2. But only 2.
One question is section A, 2 questions section B.
This would be like a section A,
This is
and this is like a section B. Yeah.
Oh yeah, so for the Kirchhoff's law, do it like
For which? Kirchhoff, yeah?
yeah, when they give us a table with microvolt and milliampere, we need to change it to base unit.
We should. It's good practice. Unless you're really careful and good with your units, you don't need to change it. But I recommend to students just to be safe and to change it.
Because some of the answers behind it say that the micro.
Oh yeah, that's fine. Like, I mean, I thought you were asking me for your calculations, do you need to change it? But there's no problem with the answer if you convert it back to milli or whatever.
Okay.
Ah, yeah. It's just for calculations, I think it's safer to convert it to full units rather than milliamps or something. Especially when you have something like VI/R, you really don't want V and I to be like 1 is milli and 1 is kilo. Because then it confuses you, and then what do you do about OR? If I said OR equals V over I, but one of them is milli and one of them is kilo, then what's OR? Something in between, So it's just safer to convert for calculations.
what is of course over there?
Across the cell, like this.
This is connected of course of there.
What? What bad English of your teacher. What did I say? Yeah, no, that's actually fine. If this is the cell and this is the resistor, connected across the cell means like this. Around it.